Hi everyone, my name is Wang. Today I'm going to present our work MAVL, Multi-Resolution Analysis of Voice Localization. This work was jointly done with Wei Sun and my advisor Professor Lili from the University of Texas at Austin. Today, smart speakers set third worldwide. For example, Amazon Echo, Apple HomePod, Google Home have tens of millions of users in the major economies of the world. And in the future, the global smart speaker will continue to grow and reach around 20 billion US dollars in 2024. With such booming market, we can add more smart features to the smart speaker. The ability to localize human voice can benefit smart speakers in many ways. For example, the smart speaker can beamform its transmission towards the user, such that enlarge the communication and sensing range. Another example is like if a user says to the Alexa, turn on the light. Alexa can tell which light to turn on based on the user's location. Similarly, a smart speaker can automatically adjust the temperature and the lighting condition of the bedroom when you go into the bed. Moreover, such context information can also help with speech recognition or natural language processing. For example, when a user says orange in the kitchen, it more likely refers to a fruit rather than the color. In this paper, we will present a novel system to localize human voice by a single smart speaker. If the user and the smart speaker have line of sight, there are direct paths and many reflected paths. As for non-line of sight, if there are some blockage like a wall or furniture, there will be both reflected paths and diffracted paths. Ideally, if we can estimate at least two paths as well as the wall positions, we can retrace the user's location. However, this raises many challenges. First, the user's voice is unknown to the smart speaker. Without knowing the transmitted signal, we cannot apply traditional approaches like channel estimation or distance estimation. So our solution is to estimate multiple angle variables. The second challenge is that the multipath signals are coherent. Coherence will cause low accuracy and merged estimation result. The next challenge is how to estimate the indoor environment. Depth sensors are not widely deployed at home, and the cameras have privacy concerns. So the best solution is to use the existing hardware, the smart speaker itself. Lastly, localizing the user in non-line of sight using acoustic signals remains an open problem due to low SNR and detoured propagation passes. To solve this, we propose our MAVL system. It consists of three major components. First, we estimate the angle of arrival coming from multiple propagation paths. Next, we estimate the room structure by emitting acoustic signals. And finally, we can retrace the paths using the estimated angle of arrival and room structure to localize the voice. Now let's first dig into angle of arrival estimation part. Let's first see the impact of coherence. This figure shows the angle of arrival profile of two incoherent signals. Different lines represent some traditional angle of arrival algorithms. We can see that there are two separate peaks at the incoming angles. Now let's see what happens if the two signals are coherent. We can see that there is only one merged peak and we cannot find either one accurate angle. So we do need to reduce coherence. We propose multi-resolution analysis to reduce coherence. Suppose we have n microphones, and the phase difference along these time series signals encodes the spatial relationship. One straightforward idea to separate multipaths is to align and cancel paths along time dimension. But it's hard to align the initial ramping up signals, and the cancellation is not accurate. If we model the multipath propagation model as T, then we find that it has three dimensions, including microphone spatial dimension, path temporal dimension, and the frequency dimension. So our idea is to utilize the frequency dimension. We can separate coherence across different frequency bands. And then we can cancel the passes by taking difference along time dimension. This is especially useful for voice signals since different pitches may occur at different times. This is the basic idea of our time frequency analysis to reduce coherence. An important decision is how to select the sizes of time window and the frequency bin to perform the analysis. We know that time is in inversion ratio to the frequency. Longer time window improves SNR, but it has more coherent signals. Shorter time window has better time resolution. At the same time, wavelet is a multi-resolution analysis. It has super time resolution. This helps us to capture transient signals in small time window, but its less energy may yield large errors. For these short time windows, we further reduce coherence by taking difference between two consecutive time windows for each microphone. All these branches are complementary to each other. In addition, the frequency of voice signals varies unpredictably over time. It's challenging to determine a fixed time window or frequency bin, so we will take advantage of them all. So basically, long time window analysis gives us stable but coarse estimation of the direct path. And the short time window analysis gives us more accurate estimation for all passes, but might have some false peaks. Wavelet analysis is extremely helpful to improve accuracy of the second pass estimation. And then we combine all the results and select the final picks by previous heuristics. Here we show an example that a woman speaks at 2.4 meters away in a conference room. The dashed red lines are ground truth angle variables of different passes. We can see that the short time window results shown as blue circles are deviated from red angles due to coherence. And the wavelet results, the yellow circles deviate from the dashed red lines due to low energy. And after taking difference, their estimation results get closer to the ground truth angles. The second step is room structure estimation. We tend to use 3D music algorithm to get distance, azimuth, and elevation angles. Since most angle variable estimation algorithms require narrowband assumption, we divide wideband signal into multiple small frequency bins and aggregate the results together. The next trick is to incorporate typical room shape. For example, most rooms are rectangular shaped, so the angle of the walls have 90-degree difference among them. We can leverage this assumption to find and correct our angle estimation. And lastly, we use beamforming to improve the distance estimation accuracy. Here is an example of the azimuth and distance profile of a conference room. The green squares are ground truths. We can see that they are separated by half pi. So we can select the corresponding red star profile peaks. And next, after beamforming, we get very good estimation of walls at the blue stars. They are very close to the ground truth. The last step is to localize voice by retracing. Using the estimated angle variable of voice and the room structure, we can localize user by retracing the passes back. Here shows two cases. The first one has two near parallel passes, which will cause relatively higher localization error. And the red one is when there are more passes. We can see that our predicted results is very close to the ground truth position. We test our system using two-sized circular arrays with 8 microphones. The smaller array has radius of 5 centimeters, which has a similar size with VLOC system. VLOC is one of our baseline approach. They use the align and cancel approach in time domain. The larger array has radius of 9.6 centimeters, which is more suitable for voice wavelengths. We evaluate our system in multiple environments, including anechoic chamber, living room, bedroom, and conference room. Here we show how we set up our system in the conference room. Let's first see the angle variable estimation results. For line offset case, the purple line is our MAVL results. Our approach outperforms all other benchmark approaches. The direct path angle variable has median error of 1.5 degrees. For the second angle variable, it has median error of 3.3 degrees. And for non-line side, the median error of the first angle is 2.7 degrees and the second pass is 6.5 degrees. Next is our room estimation results. We test different room sizes and we compare with the log system approach. Basically, they need to collect 15 commands in the room and jointly estimate the room parameters using optimization technique. Our median distance error is 2.8 centimeter, and the median azimuth error is 1.4 degrees, which is much more accurate. And more importantly, our approach is much more time efficient, which only takes seconds rather than hours. Finally, here comes the localization results. The median error is 31 centimeters for line of sight and 47 centimeters for non-line of sight. We also test for different rooms. Error increase a little when the room size increase or there are more strong reflectors. To summarize, we develop a system MAVL to localize users based on their voice using a smart speaker. Specifically, we develop a novel multi-resolution based angle variable estimation algorithm, an easy-to-use acoustic-based room structure estimation approach, a robust retracing scheme to localize the user. That's all my presentation. Thank you for listening.